So I want to just tackle a few more things, and we're pretty much done. We should be done with what we plan to cover in a Math 142 course at Queens College. We should be done with all the topics by today. I hope so. So I wanted to touch upon what we were discussing last time. Remember, we were discussing solids of revolutions, right? And the last example that we covered was an example where the solid was not revolving, the region that we sketched out at first was not revolving around neither the x-axis nor the y-axis, but by a different axis. So, and there was some confusion with the inner and outer radius. So I think we we should tackle more of these problems. So so as to develop more of a intuitive understanding. Um, so what does that look like? So let's see. So if I want to find the volume of a solid that comes from this these curves, so y equals e to the negative x, y equals 1, and x equals 2, and you revolve it about y equals 2. Revolve about y equals 2. So the first thing I would always do, right, is sketch the region. So I want to sketch my region. It's my x-axis, my y-axis. So what does e to the negative x look like? What's the graph look like? E to the negative x. What does it look like? A parabola. Oh no. No, 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 no. E to the negative x. E to the negative x is an exponential function. Are we gonna talk about this then? Exponential. Remember this? Exponential. The base here is e. And actually, what kind of exponential function is it? Is a decay. It's a decaying exponential function. So it's a function that looks like this. Something like this. Let me redraw that. And it crosses the y-axis at 1. That's e to the negative x. So this is y equals e to the negative x. The second thing that we want is y equals 1. So y equals 1 is this. That's y equals 1. Okay? Yeah. And then x equals 2. X equals 2. So this is going to be 1. This is going to be 2. This is x equals 2, right? Again, I only care about the region that's enclosed, which is this region here. I don't really care. I don't really care about anything outside of this region. However, I do care what's going to happen next. See, white. So then what do I have? I have a axis. My axis of revolution is not the x-axis nor the y-axis, but it's the line y equals 2. This is my axis of revolution. This is my new axis of revolution. So if I were to revolve this region here around this axis, then what would I get? Do you guys see what's going to happen? I'm going to have something like this. So I'm going to have like a pot, right? But there's no base. It's a baseless pot in a way. You guys see that? Yeah. It's going to be a washer method. That's right. You see that? So now we don't have to worry about maple. Now you guys can visualize this. Hopefully, you guys can visualize this on your own, right? I'm taking this two-dimensional region and revolving it around a particular one-dimensional axis. And in doing so, it creates a three-dimensional volume. And this volume can be figured out. It can be figured out by what? By establishing the fact that we have what are called washers, right? We're considering the fact that we're taking a slither, we're taking a cross section of we're taking a washer or a cross section of this volume by slicing it horizontally, I mean vertically. And in doing so, the outline of my cross section looks something like this. The outline looks something like this. Right? And this here, where is it? The center here is y equals 2. Now we have to be careful. What is the out? And this should be a lot bigger. Pardon me. This thing here, this should be a lot bigger. Right? Okay. So then y equals 2 is here. So then obviously you start to see, oh, this is a washer, and I want to figure out the volume. So in the volume, what will the volume be? You would have the pi here, right? Pi is always a part of it. Then your x values go from 0. Again, this is just look at it from the based upon the region. Where my x values go up from 0 to 2. So my integration bounds will be 0 to 2. Now the hard part is to understand what is the outer radius and what is the inner radius. To figure that out, you always have to base it upon the axis of revolution. The axis of revolution is 2. So what's the farthest what's the farthest function from this axis? Is it y equals 1 or is it y e to the negative x? Well, obviously, it's going to be e to the negative x, right? So that's going to be the outer radius. So then you have to be careful how we express that though. So this is the farthest part away from it, right? But the question now is, what is the distance from a point on the axis to that farthest graph? What is this distance called? How do I call it? Do you guys know how to express that? Okay, so now you guys see. Very good. Very good. Because what's the idea? The idea is that if I were to choose a particular x value, correct? Then this distance right here, this distance here would be exactly the y value associated with the function, which is what? E to the negative x, right? That will be that distance. But I want to figure out this distance instead, though. I want to figure out this. I don't know if I should use, I want to figure out this distance here. I want to figure out what is this? Well, if this piece here is e to the negative x, and this entire line here, this entire distance here is 2, obviously it's 2, and this piece is e to the negative x, then this whole piece right here should be 2 minus e to the negative x. So therefore, the outer, the outer radius here or the bigger radius, right, is 2 minus e to the negative x. So this would be 2 minus e to the negative x parentheses squared. Then you're going to subtract that from the inner radius. What is the inner radius? That's going to be the smaller radius, that's the distance between the axis and the inner or the closest graph. But this is easy pretty much because the graph is y equals 1. It's just a constant. So then the radius, the inner radius is always a constant radius. And the constant radius is a radius of 1 because 2 minus 1 is 1. So then this becomes 2 minus 1, which is just 1 squared. And this is dx. And now we have an integral to solve, to evaluate. So this is the hardest part, setting it up. Once you set it up, then you go on your merry way to integrate. So then you can expand 2 minus e to the negative x. It becomes 4 minus 4e to the negative x plus 4e to the negative 2x minus 1 dx. So this would be pi from 0 to 2. 4 minus 1 is 3 minus 4e to the negative x plus 4e to the negative 2x dx. And then you can go out about and start finding the antiderivative of each piece. So 3 is 3x. Then this would be what? 4e to the negative x, but then because of that negative x by the antiderivative, this will be a plus because that negative will pop out. And this becomes 4 times e to the negative 2x, and then you're going to divide this by negative 2. Evaluate it from 0 to 2. Someone made a comment. Wait, why 4e to the negative 2x? Actually, you're right. Why is that? What's wrong with me? You're right. There is no 4. It should just be positive, e to the negative 2x. You're right. There shouldn't be a 4. Thank you. Yeah. See, you guys are better. You guys are getting sharper and sharper. Very good. And so there should not be a 4 here either. So here you can write this as minus, okay? Bam. Okay, and now we evaluate. We evaluate by plugging in the values for x. And I get 3 times 2 plus 4 times e to the negative 2 minus e to the negative 4 over 2. So my answer will be pi times 6 plus 4e to the negative 2 minus, if you want to write this all in positive exponents, you get pi is equal, pi multiplied by 6 plus 4 over e squared minus 1 over 2e to the 4th. Do we all agree? And just to see what this is, we got pi parentheses 6 plus 4 divided by 4 divided by e squared minus 1 e to the 4th. So I get 20 20.4926 dot 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 dot. Right? So just to give you guys some more visualizations of this, we'll quickly open up Maple here. Has anyone actually downloaded Maple? Oh, you couldn't find it? Really? Hold on, I think something's up with Maple today. Okay, here we go. So I'm gonna put f of x as I write x negative x, and then I have just function 1, and that's gonna be from 0 to 2, and the horizontal distance from rotation of the axis will not be 2 but be 0. So let me just display the region, and that's what I get. That's exactly what we got as well. We got a region that looked like that, and then if we look at the volume, this is what we get, right? See that? There's like a hollowness to it. You can't see, it's like a ring, but it's kind of like a curved base here. And 0 to 2, that's right. And then you see the region here and the disks if you want some more visualization of it. Let's see if they have the disks. Yeah, there you go. And then of course we can fine tune it. And the more disks we add with thinner thickness, the more accurate the volume gets to become the actual volume. Now they get a different answer here. So where did we? So did I do something incorrect here? They get a different. They get 9 point something. So it must have been something, right? 2 minus e minus 1. We got the 3. 3x. We switched 3 and 4. When we squared it, it should be e positive e. Oh. Wait. No, that's fine. 4 plus. All right, let's go slow motion. So whenever this thing happens like this, whenever something like this happens, slow motion. So let me just see, 2 minus e to the negative x. That's exactly what it is. So let's see, 2 minus e to the negative x squared. This is 2 minus e to the negative x multiplied by 2 minus e to the negative x. So I get 2 times 2 is 4, and then I get minus 2 to the e to the negative x. I get another one of these, and then I get plus e to the negative x, which becomes 4 minus 4e to the negative x. And this is, of course, squared because I'm multiplying this to itself, right? And then I subtract the 1, and then I get this. I get 3 minus 4. This is so far so good. Plus e to the negative 2x. And then when I antiderivative it, I get 3x minus 4 e to the negative x divided by negative 1. This becomes plus. This becomes plus e to negative 2x divided by negative 2. This becomes a minus 2. So far, so good. And then when I plug in the 2, I get 6 plus 4e to the negative 2 minus e to the negative 4. So did I type it in wrong? Oh, 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 yeah. I missed something, didn't I? So no, this is correct, guys. This is correct. Never second guess yourself. It's just that sometimes, yeah, sometimes this thing here, this thing right here, you see how one little thing can go wrong? This must be a two. And if that is it, that still gives me something that I shouldn't get, huh? See, multiply. 6. Wait a minute, let me see. It says 9.2, 0 to 2, negative 2, 1. I got 9.525. This is 4 pi. We got 4 pi. E to the negative 2. Yeah. And then we got 4 pi. Yeah, that part is right too. But this 5 pi here, 5 pi over 2, this is the discrepancy. I don't get that. Hmm. Very interesting. Very interesting. It doesn't give me the same thing. Interesting. 4 minus 4. That's exactly right. 3x plus 3. 3x. Hmm. I don't know about this now. So actually, let's see what Maple says if I were to actually compute this. So look, this is an interface that you can use if you have Maple. This is multiplied by the integral, and you can actually put the integral. We have it from 0 to 2, right? Let me make this a little bigger. So I go over here and then the it's going crazy. Let's try that again. So this is 0. This is 2. Let me put it exactly the way we have it. So 2 minus e to the negative x squared minus 1. And let me evaluate this. Oh, I have to write this as e. I think that might be an issue. Yeah, 5 halves. Okay, so I'm getting kind of crazy with this now. Where did we go wrong? Are we missing something? Hmm. The outer minus the inner. Yeah, so I'll come back to this. There's something that's not right, but it appears everything to be right. Hmm. Yeah, we'll come back to this one. We'll come back. So there's something that's so this is correct. This portion here is right. It's just that this six here doesn't appear there. They get a five halves. So the question is how do you get the five halves? And that's something that I can't explain it at the moment. But I'll come back to this. There's a reason. Okay. So there's a reason for that. Unless you guys see it. Yeah, the method is correct. There's nothing that we did that was not correct from my vantage point.
On
The
the symbol lab, I don't know, it shows pi times 2 plus 4 over e squared plus e to the fourth minus 1 divided by 2e to the fourth. I don't know if that helps.
uh not so much. There's something about four. Yeah, so something about this four and this one. I'm not too sure why there's a discrepancy with with the I don't know. Hold on. Is there something? Two times two is four. Minus one is three. Am I crazy? I don't think so. Oh boy, oh boy. Boy, oh boy. Guys,
Oh,
why did you let me do this? Why did you let me do this, say these things and say, yes, this is correct? Why do you guys believe me? Where do you guys think I messed up? Now I can't believe I did this. It has nothing to do. Look, guys. It has no, like that's why I was going crazy because I'm like, we did everything right. We did all of this right. We did the washer method correctly. We're doing this. The antiderivative is perfect. There's nothing wrong. There's something that I just overlooked and overpassed, and everyone did the same thing because it's so commonly done. No, we didn't forget to do the one. We didn't miss the one. There is no one missed. You know what we forgot to do? We forgot to identify the fact that there is a zero as an integration bound. And what normally happens? We have the antiderivative, right, of a polynomial, and these x's appear. And when you plug in the zero, everything just magically cancels. And this is what I also assumed. Oh, we're gonna plug in the zero is gonna be zero anyways, but that's not true. That's not true. So you have to be careful with that. So actually, that is the reason why it's not the way it's not the five halves doesn't appear. So watch what happens when we do it. You see, guys, everything has a reason. Everything has a reason. Okay, so then I'm gonna include now, as I should have in the beginning, I'm gonna include what happens when we plug in zero. Things don't cancel. Of course, I subtract. This guy does cancel 3 times 0. But then this becomes 4 times e to the zeroth power minus e to the zeroth power over 2. Now I feel a lot better. So you see these things happen in real time. This is 6 plus, okay, I get the same thing, right? 4 over e squared minus 1 over 2 e to the fourth minus 0 minus 4 times e to the 0 is 1. E to the 0 is 1, so it's minus 4. And then e to the 0 is 1 again, but over 2, this is going to be a plus. This would be a plus a half. Do you guys see that? And then all is well with the world. 6 minus 4 is 2. 2 plus a half is 2.5, 5 halves. So yes, yes, I agree. I agree, Maple. I agree. What is it? SimLab? SimPyLab? I agree. This is what it said. It was uh what was it? I don't see it. 9.5 or something, right? You see, guys, everything's okay. Just be careful. Don't be like me. Don't do what I do. Don't just disregard the zero, especially not when you have exponentials. Because when you plug in zero, it doesn't become zero, it becomes one. See, all these fundamental little things still apply. Okay? All right. Okay. So just we're good now, right? Okay. So let me do one more of these, but this time I'm not gonna rotate around the horizontal line. I'm gonna rotate it around a vertical line. So what if I have an example where I have an equation here, y equals x, and I got y equals square root of x, and I want to rotate this, so revolve around x equals 2. So again, sketching it is the important thing, right? Y equals x is just a horizontal line that looks like this. That's y equals x. And then you got y equals square root of x, and the square root of x looks like this, right? And of course, I only want the region in between, and the region in between is this one here. Now, now the difference here is that I'm going to revolve around the line y x equals 2. So if you guys know, if you were to set it equal to one another, you should know that the intersection point here is 1 comma 1, right? This is 1 comma 1, right? But now my axis of symmetry, or my axis of revolution is this one. This is my axis. X equals 2 is my axis of revolution. Now, what happens if I revolve this region around this axis? What would I get?
Cool.
I'll get something like this, right? I'll get like a dome in a way. I'll get like some kind of dome here, but hollowed out. You see that? It almost looks like a flying saucer kind of deal. And now, what is this now? How do I find it? I have to find washers, right? But now my washers are sliced from a horizontal point of view and stacked vertically. So now I have a washer that looks like this. I have a washer that looks like this. Right? Sorry about that, Jerry. I'm gonna mute you. So that's my washer now, right? This is my washer. But the same thing applies. The same kind of setup. What's the setup? Pi. Now, because my washer is stacked vertically, I have to see what's the range of the y values. And the range of the y values, right? My range of the y values is from 0 to 1. It's this region here. So my y values only go from 0 to 1. So this is going to be 0 to 1, and this is going to be dy, right? Now the hard part is to understand how do we express the outer versus the inner region of a radius. So then what is the outer radius? Meaning what is the function farthest away from the axis of revolution? So if this is my axis of revolution, what's farthest away? Is it the blue or the pink? Obviously it's going to be what? It's going to be the blue. Now, how do I express that distance? It's not going to be in terms of x. It's going to be in terms of y. So actually, I don't want to write it as y equals square root of x. I want to write it as x equals y squared because it's a function of y. So at a particular y value, you see this? At a particular y value, the horizontal distance is represented by x. So this here is going to be x equals y squared. That's that distance, right? This distance here. But I want to find this distance here because this is the outer the biggest radius, the bigger radius, the outer radius. So how do I express that then? How do I express the outer radius? If this piece here, do you see this again? If this piece here is y squared and this whole thing here is 2, then the outer radius would be what? That's right, David. It's going to be 2 minus y squared. Does everyone see that? That's this distance here. That's this distance here. If this is if this piece is y, at a particular y value, my x value is y squared. From this distance here, if I take away from 2, gives me the rest. And now how do you get the inner? Same idea. Now at a particular y value, what's the x value? It's going to be exactly y equals x, x equals y. So it's going to be y. So this distance here, if I were to draw this like this distance here is exactly y. But this entire thing, this entire distance here is 2. So if this is y and this whole thing is 2, then the inner here would be what? What would be the inner radius or the smaller radius? How would you express it? 2 minus y. That's right. So guess what I have? I got 2 minus y squared minus 2 minus y. No, 2 minus y squared, parentheses squared, minus 2 minus y squared. And this is my setup. That's my setup. So then what's going to be my volume? Pi from 0 to 1. 2 minus y squared is going to be what? 4 minus 4y squared plus y to the 4th minus parentheses 4 minus 4y plus y squared dy. And now we can see if we can combine like terms. This is 0 to 1 of 4 minus y squared plus y to the 4th minus 4 plus 4y minus y squared dy. So the 4's cancel and the y squareds combine, and I get y to the 4th minus 2y squared plus 4y dy 0 to 1 pi. And y to the 4th, I get y to the 5th over 5 minus y 2y cubed over 3. plus 4y squared over 2, which is the same thing as saying 2. I evaluate this from 0 to 1. And I get what? Now this is the case where you can plug in 0 and nothing happens, so we don't have to worry about this time, right? We're not going to make that mistake twice. You're missing the 4. Four. Where am I missing the 4? 4 minus... Oh, I'm missing the 4 here, right? You're correct. So this should not be... This should not be negative 2. This should be what? Negative 5, right? Thank you, Justin. Should be minus 5y. And then this should be what? This should be 5, right? 5y cubed over 3. Thank you. So this becomes 1/5 minus 5/3 plus 2. And then if you want to write this as a fraction, this would be 3/15 minus about times 5, I get 25 over 15 plus 30 over 15. And then this becomes pi times negative 22 plus 30 over 15, which is 8 over pi, 8 pi 15. Okay. And then let's just make sure everything's okay. This becomes 8, 8 pi, and this is 15. So it's 1.675. So 1.675. And just to make sure there's no funny business here, let's just go back and ask the all-knowing Maple what what it thinks about this stuff. So you got Maple here, and then my functions are going to be I can still write it as x and square root of x. That's okay. They're going to do things a little differently than we do, but that's fine. And then a and b, we have it from 0 to 1. And my vertical line of revolution would be at 2. And let me just briefly get the region. So if we get the region here, this is exactly what we got, right? And if we get the volume, what do we get? We get this. We get this guy here. See that? And if I want to get some shells in the mix, that's what it will look like. Pretty cool, right? Well, that's what they use shells. Well, we use the same thing, washers, but they it's a little different. The shell method is a little different in terms of the setup. And we get the same thing. We get 8 pi over 15. So we're good. Okay. Yeah, it does look like Jello, huh? Yeah, you can make your own Jello by using solids of revolution. Look at that. Calculus is everywhere, even in food. Jello food. Okay, guys. So great. Great. All right. So do we feel more comfortable with solids of revolution, particularly when we talk about solids of revolution where the axis is not the x nor the y? So now you see that it doesn't matter what axis I use as long as I can express my radii correctly. If I can express my radii correctly in terms of the x as functions of x or as functions of y, depending upon how I revolve it, whether horizontally or vertically, that's the hardest part. If I set it up correctly, then everything should go uh, as it should go. Okay. Okay. So one uh one last thing. Actually, there's gonna be two more things, but I think we can finish one of them today. There's something that I want to talk about that's kind of related. It's kind of related to, it's not related to volumes anymore, but it's still related to integrals, and it's called arc length. So this is an important idea. Um, I think it's a pretty cool idea too. It's not as cool as volumes. You've seen this monster before. But this idea of arc length is very interesting, especially this whole idea of volumes too is interesting, especially when you step into the multivariable scene. So for those of you who are continuing with 143 and then plan to do multivariable, I think that's where really calculus comes in even to more life, because it's seen from a three-dimensional point of view, and that gets really interesting. But for now, we're gonna still stick with our two-dimensional world, and so it goes something like this. Like we have a graph, right? So far we've been discussing how to figure out the area underneath the curve, right? So we figured out how to do that, and we did that through integration, which is cool. And then we seen that of different kinds of functions, and then we also saw functions how to find the area between two curves, right? We saw how we can just take the points of intersection and then integrate over the difference, and then you find the area. So we saw that as well. We just saw recently that you can revolve this thing, right? And you can find the volume of a solid generated by the region being revolved around the x-axis. And then similarly, you can also do it the y direction, right? So we're starting to get more, I guess, more in tune with how we can exploit the graphs of functions. We can exploit it in various ways, which is now this is not just any random curve. You can actually generate solids and volume, which is awesome. Okay, now if you're curious, you'll be like, okay, so I can do that now. I can integrate, I can find the areas, I can find volume. Awesome. And now there might be the question is how, if I were to actually, let's say I had this graph here and I actually wanted to reproduce the same graph physically. The question might be how much material, how long of a, let's say if I wanted to use a string to represent this, how long should that string actually be so that it fits here from here to this point perfectly? So that becomes like, how do we do that? Now let me ask you guys, how, given the ways that we have approached finding the area under the curve, finding the volume of a curve, of a solid, how do you think we're going to approach finding the length of a curve? Remember, think about approximation. How do you think we can approximate this? So remember when we talk about areas of curves, what do we use to approximate? We use things that we know. Rectangles. Okay. And then when we did volume, what do we use? We use cylinders. Okay. Now, how do you think we're going to approximate curves, the lengths of curves? We're not going to use rectangles because rectangles represent areas. What do you guys think? How do you approximate curvy paths? I want you to really consider this and see how you can also by yourself. Tangent, huh? Oh, tangent. That's a good idea. That's a good idea. But how do we, let's say we didn't know about calculus and we didn't know about tangents. What's the thing that precedes tangents? what's the I think the word is the predecessor of tangents. Remember when you talked about derivatives? Before we talked about the tangent line, we talked about what? Not the tangent line, but the blank line. It starts with an S. It's not slope. Nobody? Thank you, Samantha. Thank you. Secant. You guys see that? Like, what if we divide this up again? Really tiny pieces, right? Into tiny slithers. But then what do we consider? We consider we consider what? Small secant lines. Do you guys see this idea? It's the idea that matters. Yeah, Moses, we're using little line segments. And what do you think? The smaller the line segment, the more accurate the length will be. Doesn't that make sense? Like, wouldn't that make sense given everything we've been doing? We've been using rectangles to find the area underneath curves. We've been using cylinder discs and cylindrical washers to find the volume of solids. So then wouldn't it make sense to make this curve into little pieces? And those pieces are maybe just little straight line, little line segments. And wouldn't it make sense to add up all those line segments and let those number of line segments go to infinity, which would indicate that their thicknesses become infinitesimally small, and so on and so forth? Yeah. So like the more line segments that you create, the shorter they will be, right? And eventually at infinity, which is the beautiful idea behind calculus, it forms into the integral. So guys, it's about the idea that matters. Like, I could have just told you what the formula was and move on. I could have really done that. But I don't want to do that because I want you to see it. I want you to see it for real. So like let's look at a particular graph here. So let's say I have this here, right? Let's say I have this like curve here. And then I have this segment here like this, right? So the idea is this, guys. The idea is this. This is a right triangle. You can set this up as a right triangle. And you can say this is what? Some change in x. And this is going to be some what? Some change in y, right? By Pythagorean theorem, what would this have to be? Some change in distance. I'm going to call this change in s, okay? Now, change in s, this distance here is, if you make these smaller and smaller, right? If you make these smaller and smaller, this distance here becomes very close to the actual length. And agreed? It becomes really, really close. So then how do I represent the change in s? Isn't it the square root of the change in x plus the change in y? And this is squared, sorry. Do you guys know what this formula is called? This is called the distance formula. Remember the distance formula? Remember the distance formula? It's the change in x squared plus the change in y squared. Take the square root of that. That's the Pythagorean theorem. The distance formula is the Pythagorean theorem just expressed in the coordinate geometry, analytic geometry. So then how can I represent this here? I can rewrite this. You guys see how I can rewrite this? I'm gonna factor out the square root of x squared. So if I factor out the square root of x squared, right? What does it become? It becomes 1 plus the change in y over the change in x. So there's a little bit of derivation here. And then, do you guys see how I factored out the change in x squared? I factored it out from both the change of x squared plus the change of y squared. And this is what I get. So then if I take out the square root of x, if I take the square root of change of x squared, I get the square root of 1 plus the change in y over the change in x squared multiplied by the change in x. This is the change in y. This is the change in s. Again, the change in s is the approximate length of curve, of, I would say, piece of curve, of piece of it. So I have one piece. So what am I going to do to approximate the whole curve? So to approximate the whole curve, what am I going to do? Approximate whole curve. What am I going to do? I'm going to take the summation of those. I'm going to take the summation of these change in s's, which is the same thing as saying the summation of what? The change in 1 plus the change in y over the change in x squared, right? Times the change in x. Now, what do you think I'm going to do after this? And I'm going to say this goes from I to n. I do n times. But I want the exact length, right? Approximate length. Now I want the exact length. How do I get the exact length, guys? What do I do? What's the magical thing that we do every time? What do I do? I use what? I use the limit. Take it to the limit. The limit. I'd say, hey, make n go to infinity. Make it go to infinity. I want an infinite number of these. I can do that. What happens when I do that? This becomes a Riemann sum. This is a Riemann sum. Now you tell me, guys, what do I get at the end of this limit? What do I get at the end of this limit? What is it going to look like? It's going to look like what? When you take the limit of a Riemann sum, you get what? It starts with an I. No, you don't get the area. You get the integral. That's right. You get an integral. And where's the integral going from? What are my bounds of integration? From A to B. Of what? The square root of what? 1 plus, what's this? What does this become? We know that this becomes dx, doesn't it? But what does this become? What's change in y over change in x become? Doesn't it become dy over dx squared? But hey, what in the world is dy over dx? Isn't it y prime? Or in other words, the function prime, the derivative of the function? So guys, this is the arc length formula. So the arc length formula of a function is given by a to b of the square root of 1 plus the derivative of f dx. And this is it. That is your formula. And the reason for this formula was just outlined here. Using the distance formula to approximate curves through secant lines. So for each interval, I have a secant line. For each interval, I have a secant line. And the smaller the more partitions that I make, the smaller those secant lines become. And at the end, at infinity, as you take the limit, the sum of those small, infinitesimally small secant lines is the actual length of the curve, which is, I think, beautiful if you think about it. This idea has been applied in 3 different variations. One is for the area underneath a curve. We use rectangles to approximate. Then to find the volume of a solid, we use smaller disks. And now we're using pieces of lines. But do you see the idea has not changed? It's just been expressed in 3 different variations. So that's like the more abstract way of looking at these things. Cool, right? What do you guys think about this? Cool stuff or what? It's a cool way. Yeah, it's a pretty interesting way. So let's see this in action. Let's see if we can do this in action. So what if I have a function 1 plus 6x to the 3 halves, and I want to know what's the length of this from 0 to 1. So we don't have to go through all of it, but we can just set it up. Yeah, Moses, that's exactly. That's the way life goes. Things come back and they make full circle, and then once you see it, once you really see it, it makes sense forever. And then you're like, "Oh, I get it." So then how do you set up to find the arc length? Well, this is going to be my A, this is going to be my B from 0 to 1. Take the square root of. Now I'm going to take 1 plus, what is the derivative? Because this is really f prime, right? So I have to find a derivative. So what's going to be the derivative? This is going to be 6 times 3 halves x to the 1 half, right? And I'm going to have to square this as well. So let me just get this. This is 3, this is 9. This is x to the 1 half power. So this is 9 x to the 1 half power squared dx. And so this will be from 0 to 1, square root of 1 plus 81x dx. And then you would go about um, evaluating this by setting u equal to 1 plus 81x, and then du is equal to 81 dx, and then that means that 1 over 81 du is equal to dx, and so on and so forth. Okay, but I'm not gonna continue with that. So we're done with the arc length portion.